great pleasure. This is my first visit to Brazil, and I'm enjoying it very much. Thank you. I know that English is a second language for many of you, or for most of you, and therefore, if I'm going too fast, if something is not clear, please stop, and let's make it an interactive session. So if you have any question, you can raise your hand during the tutorial, and don't be afraid. Alright, so this is about, in computer system performance analysis, we talk about many things. In particular, we talk about measurement, we talk about simulation, we talk about modeling, analytical modeling like queuing theory. However, when I was writing this book, and I was at Digital Equipment Corporation for 7 years, working as a performance analyst in the field, and I had a PhD in performance analysis from Harvard, I realized that one field which is really missing from the whole performance analysis area in computer science is the design of experiments. And this is very valuable and useful area, and therefore I think mine was the first book to talk about design of experiments as applied to computer science. So that's what this particular lecture is about. And so basically, whether you do measurement or simulation, one of the questions comes up is, how much measurements should you do? How many combinations should you measure? Right? If you are doing simulation, the question comes up is, what parameter values should you use, and how do you combine all of them? So for example, if you are measuring performance of a network device, firewall, or maybe proxy server, router, anything, then you need to worry about the performance is affected by the processor that is used, by any storage that is used in the system, network card speeds, packet sizes, and each of these factors has many values. For example, the CPUs could be single core, dual core, multi-core. This could be different speeds. Networks could be many different speeds. Packet size could be many. Now the question is, this is just a small list, right? And if you were to do all possible combination, in this simple example, they become 144 combination. And the combination could be too much. So there are two problems with this. First is, generally the number of factors and the values that they can take is very large, and we don't have the time and the resources. We might have the time, but we may not have the resources like computers and people and so on and so forth to run all of that combination. And the second problem is, even if we run all of those combinations, how do you find out the effect of each factor? So those are the two things that are covered by experimental design. And as the title says, the experimental design is not just for computer networks or anything. It could be used for anything. If you have an algorithm that you have developed for your research, that algorithm may have different parameters that affect the performance, and you want to find out which is the most important parameter, right? Or which are the combinations that we should simulate, which are the combinations that we should measure. Again, experimental design can be used. So you can use it for databases, distributed systems, robotics, anything that you have. So this techniques that we are going to discuss in the next 3.5 hours are general enough to be used with any field. Alright? So what does experimental design do? It allows you to design a proper set of experiments. So I will show you some examples as to what does it mean, the proper set of experiments. If you did all combinations, that is one possible set of experiments. That is one design. Okay? But there are other designs that will take much less time, and that will actually produce almost the same amount of information. Alright, so how do you find those designs? So that is the first thing it does. Second thing that we do with experimental design is we can develop a model that really tells you how the data relates to different factors. So finding the correct model. Third thing is finding the effect of each of those factors. And I will define exactly what we mean by effect. And generally in the real world, when you go out and you do analysis, they don't have infinite money. So what they want to do is, they want you to spend money, or they want to do the rest of the stuff on the most important parameters. So suppose you have a system which depends upon 7 different factors. You probably cannot change all 7 factors. In the previous example, we have CPU and the distance and so forth. But suppose the analysis says that really the most important thing is the type of the network. Then changing the CPU is not going to help you. Right? So that kind of information can come from experimental design. Isolate the measurement errors. So you have decided to measure and analyze the performance based upon 3 or 4 factors, but there are tons of other factors. There are dozens of other factors that you have not controlled, such as the room temperature, the weather, the user, the person who is using it. So there might be several factors. All of those show up as errors. They show up like noise. We call them errors. So we have to find out how much error there is. Right? If it turns out that 90% of the data that you have gathered is error of noise, then clearly you haven't done a good job. Because you have only used the factors that affect only 10% of the performance. So we really need to know how much is the effect of the factors that we are controlling and how much is the effect of the factors that we are not controlling. So that can be done. Estimate confidence intervals of the model parameters. And every number that comes out of the measurement is a random number. That just one instance, if you were to repeat the experiment, the number will be different. Right? So if it is a random number, then we talk about the range. We talk about the 90% chance that it will lie between 1 and 20. And we call it confidence interval, right? So the question is, if the confidence interval is so wide, say I told you that, well, I think the performance will depend upon the CPU, but the effect would be somewhere between 1 and 2000. So the person listening to me will say, well, that doesn't look like any useful data to me. 1 to 2000 is a big range. Can you narrow it down? So the question is, how do you narrow it down? Right? How can you put more confidence and say, no, I think more like 100, not 1 in 2000, right? So, confidence intervals. Check if your alternatives are significantly different. And oftentimes, if you don't use the confidence intervals, and if you don't use it correctly, people might get a wrong impression, and they might say that this is better than the other, A is better than B, when actually A and B are really very similar, they're just randomly different. Right? So to figure that out, check if the model is adequate, and so to find out whether this model is good enough. So we'll talk about all that in the next 3 hours. And this is basically, as whatever we talk about, as I said before, it applies to any system. Alright, networks, distributed systems, databases, algorithms, and it might be good to just get a feel of, for me, as to what you guys are working on. And also I want to make it a little bit interactive. So first of all, I know everybody is working on networking here because you're here for a networking conference. But anybody who is working on difference other than networking, anything other than networking? Raise your hand if you're working on something different than networking. Okay, sorry. What are you working on?
Distributed system.
Distributed system, that's a good example. And I want other people to also tell the same similar thing so that we open up a little bit here. Everybody just networking, that's it? It can't be.
PBX, private branch.
Private branch exchange, PBX. Yeah, telecommunications and performance, yeah, that's good. There I see a distributed systems person, another distributed algorithms person there. Yeah, so the idea is that any field can use these techniques. Okay, so with that, I just want to start with this cartoon. And the cartoon says, if this doesn't help, don't worry, it's a placebo. So the idea is that this field of experimental design is used in medical field a lot. In the medical field, whenever they do any experiments, they take 50% of the patients, they give them placebo, and the 50% of the patients, they give them the real thing, right? And then they can compare whether the medicine has any effect, right? Similarly, it is used quite a bit in agricultural field. When they want to find out whether this fertilizer has an effect, that fertilizer has any effect, they put different kinds of fertilizer and they take some part of the land which has no fertilizer and then they compare. Alright? So we need to do the similar things in computer science. As I said before, much of this was missing from computer science totally. Most of the computer science people were not aware of these. And when we first applied it, so I said, okay, let's apply it, and my students applied it, and then we found some problems as to what the problems that we can run into computer science. So we'll talk about those problems as well. Alright, as Nelson announced, all of this is in this book that basically is the first book that's talk about experimental design, and the book is available outside, but some of you already know the book. And so basically this is chapter 16 to 20 through 19 of this book that we're going to cover. So the very first, so there are 4 modules in this 3 hours. The first module we talk about just introduction. The second module is about 2 raised to k factorial design. And obviously I will have to explain what does 2 raised to k mean. Then we talk about 2 raised to k r factorial designs. Then we talk about 2 raised to k minus p fractional factorial designs. And I think that will give you a pretty good idea of what this field is about. And the book talks about 3 more chapters after that, but we don't have time to cover all that here. But it will give you a good idea as to where it can take you. And by the way, I am recording the complete audio and video. So this will be available online at this URL, which is on every slide. And in fact, I mean, if you forget, you have some of you have a handout. So the handouts have the same URL listed. And so 2 or 3 weeks from now, you will find the whole audio video stuff online as well. Okay. Any questions so far? Any comments? So let's just move on with module 1, which is just the introduction to what is experimental design, what is factor, effect, and so on and so forth, what are the common mistakes, and some sample design. So this is just the introduction part. And so we will use these terms, factors. So anything that affects the performance, we call it a parameter in our design, but only those parameters that we are going to control, we call them factors. So the performance might be affected by a dozen parameters, and we want to control only 2 of them. So we have 2 factors. Alright? So anything that we don't control, those we will not count the factors. So factors could be CPU type, memory size, number of disk drives, workload used, user's educational level. You know, there are so many things that could affect the performance. In other books, they call them predictor variables or predictors, but we call them factors here. Levels. Levels are the values that the factors can take. So for example, if you have a CPU type, then you will have to put, there are 3 different CPU types, then you will have 3 levels of the CPU. Or if you have 4 different disk levels, 4 different disk types, then you have 4 levels of the disk. Alright? And other books and other fields, they talk about treatment. They call medical field, they will call them treatment. In agricultural field, they call them treatments. Obviously, that makes sense in their field. In our field, it's better to call them levels. Okay? Replication, repetition of the same experiment. So if you take the factors and use same values and run it again, that's a repetition or replication. Alright, why do you want to run it again? Because there are many factors that you do not control could have changed the second time and the number will come out different. The same applies to simulation. If you run the simulation second time, because you have a different random number generation, different random number seed, the results will come out different. Right? So you do multiple replications. Design. A design is actually the experiments in which you tell every factor that you're going to change, what values they're going to take, and so the whole set of those experiments is called a design. And to start with, we have something called full factorial design. A full factorial design is one in which you take all the factors at all the levels. So for example, if we had one of the previous examples and we did it for three levels for the first factor, 3 levels for the second factor, 4 levels for the third, and so on and so forth, for 5 factors, this itself will come out 324 experiments, and if you were to repeat each experiment 5 times, you will have to run 324 times 5 experiments, which is a large number. So full factorial design is one possible design. However, generally it is too big. Generally it is just too many experiments. And if it is not, then somebody who is funding this study will say, oh, only 2 experiments, why don't you do this factor, that factor, that factor? So the list of factors will keep increasing until you run out of time. Right? So full factorial design is possible, but generally not desirable, because we can do much better with less number of experiments. So let's just see one more graphical interaction. So here's an example. We have 2 factors, A and B. When A is at level 1, the performance is 3. When A is at level 2, the performance is 5 if the factor B is at level 1. On the other hand, if B is at level 2 with A1, the performance is 6. And with A2, the performance is 8. Simple experiments, 2 by 2. 2 factors, each of them has 2 levels. We need 4 experiments. We can do all the combinations. We did the 4 combinations and we found these numbers. So how do I summarize this result? You see, every time I go from A1 to A2, the performance changes by how much? 2. Whether it is B1 or B2 doesn't matter. Right? When B is at 1, you go from A1 to A2, the performance goes up by 2. When it is B2, performance goes up by 2. So we can say that the effect of factor A is 2. Similarly, let's look at B. What is the effect of factor B? 3. Because when you go from B1 to B2, the performance changes by 3 regardless of what A is. So this is a very good system. There are 2 factors and we can say that the factor B has effect 3 and factor A has effect 2. Now if you want to work on this problem more, you want to improve the system, what is it that you will put your money on? Factor B, because it has more effect than factor A. Alright? So we can analyze the system like this very easily. However, let's think about this other system. In this system, we did the same 4 experiments and the performance came out 3, 5, 6, 9. So now the question is, what is the effect of factor A? Now let's see. It is 2 if it is B1, it is 3 if it is B2. Right? So we cannot just make a statement about A. We have to say, well, depends. For A, you have to tell me whether B is B1 or B2. If B is at level 1, then the effect is 2. If B is level 2, then the effect is 3. Alright? So you cannot make an independent statement about factor A. Similarly, let's look at B. What is the effect of B? B effect is 3 if A is at level 1 and it is 4 if A is at level 2. So again, we cannot make a statement about B without knowing what the effect A, what factor A is. Alright? So this is called interaction. This is the part which depends upon both factors. So in this case, one has to say that there is an interaction between these two factors, and that interaction does make an effect difference of 1 actually at least here. Right? So this is interaction, and we'll see how to analyze interaction in a minute. But now we know these terms. So we know the factors, levels, replication, design, and actually we know also the word effect, although I did not put it here, but explain that. Effect and then interaction. So effect is something that just depends upon the factor alone, and interaction is something that you have to combine many factors into and make a statement. Alright. So with that, we are going to talk about what is, if you didn't know about experimental design, which hopefully many of you are learning for the first time. If you don't know experimental design, then you might have problems like this. First of all, you may not be able to say anything about experimental error. You cannot say what is the effect of the factors that you didn't control. Alright? Second thing is, you may not actually be able to figure out which factors are important or which parameters are important. Generally, in the real world, the number of parameters is very large. The effects of different factors are not isolated. So even though in this simple case, you could isolate A and B, but in many cases, you don't even know how to isolate. How do you say, when you did such a big set of experiments, how can you say that what is the effect of this one factor? Simple one factor at a time design are used. So one factor at a time design means what you might do is that you will take some value of the parameters. You will say, well, we'll start with one CPU, one disk, and this and that. And then I will just change the CPU to the second one and see what is the difference. Then I will change to the third CPU and see what is the difference. So you do one factor at a time. Right? That analysis can produce very misleading results. So for example, here, if you would have done one factor at a time design, what you would have done, you would have started with 3 and said, okay, let me change, we will start with this central case of A1, B1, and let's change A to A2, A1 to A2, sorry, A to A, level 2, and the effect is 2. You can make that statement. However, that statement is false because you didn't try out the combination B to A2, right? Similarly, then you will do the combination for B, you will change B from 3 to 6 and the effect is 3. And again that statement is false because you did not do the other combination. So the thing is, if there is a lot of interaction, one factor at a time designs do not work out. Or you might just do all the combinations, in which case you have done too many experiments. So the best way is to do 2 phases. The first phase, you take lots of parameters. So you can take 10, 15, 20 factors and put each of them at 2 levels. Just 2 levels. Although the factor might have many more levels, but you just assume that 2 levels, and that works in many cases, it doesn't work in some cases. So first you do that. And then you try to figure out which factor is most important. Alright? So you find out that the top 2 factors are these, the top 3 factors are these. Then with those 3 factors, you do lots of levels. Alright, so that way you don't miss any intermediate points. So with that, you will be able to get almost the same amount of information with less number of experiments. So to summarize, what we have already learned so far is 2 designs. One factor at a time design, which is called simple design, vary one factor at a time. If either factor has ni levels, then it will require 1 plus ni minus 1 sum. of all of that many experiments, and you can apply this to the 2x2 design that we had. There we have 2 factors with 2 levels each. In that case, you will end up running 3 experiments, because you will do the central place and then you will change A and you will change B. That is 3 experiments. This is not statistically efficient. What that means is that there is a lot of statistical information that is missing from this, and if you were to do 3 experiments, there might be better 3 experiments than those. So you are not really making full use of your time. Alright? So that's another thing we'll see in the other designs that we will study later on, is that by doing proper design you can get more information. Another way to say this is that if you use this 1 factor at a time design, your confidence intervals, if you do come to that point, they will look very wide. So your statements will be very, very loose statements. You can say the performance of A is somewhere from this to that. Alright? Statistically efficient means you can be very narrow. You can make a statement that I'm 90% confident that the performance A is from 10 to 15. That's much better information. So that is statistically inefficient. Wrong conclusions if the factors have interactions. So that's another thing, is that you're totally ignoring the interaction in this simple design. And as you saw in the second example there, that it is not recommended if there is interaction. Other extreme is full factorial design, where you do all possible combinations. Now the question is that, okay, so first of all you need a lot of time, and it will cost a lot of money, and then generally we don't know how to calculate the effects. So that is one reason. But again, if you can calculate the effect, then better thing is again to do that 2-phase design, where you first do 2 levels and then continue to more levels. So the next type of design is called fractional factorial design. And that's what we actually want to finish this course and this tutorial with, is that if you don't want to do full factorial and if you don't want to do simple design, then what is in between, so that you can get the minimum number of experiments and the maximum information. And that's what we need to, from here, if you get out from this room, at least that is something new that you would have learned today, is that you really don't need to do all the possible combinations and still get something useful. Alright? So how to get the maximum information with the minimum number of experiments, that's the whole purpose of experimental design. And that can be done very easily with the fractional factorial design. So it saves time. It may not get all interactions, not a problem with negligible interactions. So there are some negative sides to this also, and we will see that when we get there, that fractional factorial designs are good as a starting point, but not as the final point. You really have to check out and see if you got the right information. Okay? So here's an example. So if you have a personal workstation, now these processors we don't use anymore, but it doesn't matter whatever processor you use. So you have 3 types of processors, you have 3 memory sizes, you have 3 disks or 4 disks, and you have workloads of 3 different kinds, secretarial, managerial, or scientific, and the users are of 3 different kinds, high school, college, or postgraduate level. And for this workstation, if you were to do the analysis, you will need, again, as we saw before, 324 experiments. However, okay, so if you were to just limit to 4 factors, not the one which has 4 levels, which was the 4 one was number of disks. Yeah. So if you just were to leave to 4 factors, each at 3 levels, generally the full factorial design you will need 81 experiments. However, in a fractional factorial design you could do with 9 experiments. So here is a design in which we have listed 9 experiments, and these are the combinations. This is the CPU, this is the memory, this is the workload, this is the educational level. And if you carefully look at this combination, you will notice that we have tried every CPU with every other levels of the other factors. Every memory level is combined with other factors. So this has been very carefully designed such that we have gotten almost as much information as if you would have done all the combinations. Although the number of combinations is only 1/3. Instead of 81, actually 1/9. Instead of 81, we are just doing 9 experiments. Alright, so how do we write a combination like this? So that is something that we will talk about later on in this one. We talk about fractional factorial. But this is a fractional factorial design. And we would call this design as 3⁻⁴ - 2. Because there are 4 factors. Normally they will take 3⁻⁴ experiments. But we are doing only 3⁻²⁴ experiments, which is 3⁻⁴ - 2. Okay? Alright. That finishes the first module, and we are going to go to the second module. And the summary of this module is that the goal of experimental design is to get the maximum information with minimum number of experiments. Alright? And then we define the terms. So now we are going to use this quite often, and so please ask me if something is not clear to you. You can propose a problem yourself, and we can discuss what the factors are. So we talk about what is a factor, what is a level, what is a full factorial design, what is a fractional factorial design, and we talked about interactions. Any questions? And it will be good if somebody asks a question, because that way it will open up other people to ask the questions too. So far there have not been any questions. So anybody has any question about anything we talked about? Yeah, go ahead.
An analysis that is based only on a number of experiments doesn't consider the amount of processing that is required by different experiments, by different runs. So like the population size and so on. Is there any way that the size of a single experiment can be considered?
Okay. So question is, I will repeat the question. The question is that in this system, in addition to the number of experiments, we have sometimes factors, and we gave a good example, the number of population size that has to be selected. Say for example, you are doing a survey, then you need to figure out how many people to survey before you can make any conclusion. Right? That's the question? Okay. So the answer is yes. Basically, one of the things which is independent of all this is that when you calculate the confidence interval for any experiment, that clearly depends upon how long you have done the simulation, how many people you have surveyed, which is exactly the same thing. So that length of the simulation we didn't talk about here. We just talk about number of experiments, but each experiment could be so short, or each simulation could be so long, right? So the question is, what is the length of the simulation? And that shows up in the confidence intervals. So today, although we are not going to talk about that, but I want to summarize that is that there is a whole discussion on as to how long is the simulation good enough, or what is the size of the population which is good enough. Clearly, there are formulas that give you the confidence interval as a function of the population size. And so, depending upon how confident you want to be, you need to survey that many people. Okay, I need to run the simulation that long. And now here is a real interesting thing. Now that we talk about this is totally different chapter. I want to give you an example there. On the television, every day they show you a survey. They say, well, we surveyed and I found that 55% of the people are going to vote for candidate A and 45% are going to vote for candidate B. And the sampling error is 3% or 4%, something like that. They don't say that if the sampling error is 5%, then 55% is same as 45-50%. 50 plus minus 5 is almost the same thing. Right? So the confidence interval depends upon the sampling error, and that is as wide as the difference. Right? So what they did was, when you do simulation, when you get a sampling error like 5%, just look at the number. 3 to 4% is very common on the television. That simply means that all they did was interviewed something like 33 or 40 people. And they're making a statement about 40 million people. Right? So unless their sampling error, the confidence interval is very, very small, actually it has to be much less than the difference that they're trying to compare. So that's where, so there is a whole formula for how many people you should survey before you. So the confidence interval depends upon the number of people surveyed or the length of the simulation. That's an orthogonal factor, and there are formulas for that will tell you. So here we are just going to talk about the number of experiments. The length of each experiments, yes, you have to, when you run the experiments, you will find out how much randomness there is. Okay? All right. Any other question? That was a good question. Thank you. All right. So we will move on to the next module, where we will talk about full factorial designs. And then we'll talk about how to analyze it. So full factorial designs will start with just 2 factors and 2 levels. We'll see how to do the modeling, how to compute the effects, and then some very simple method, and then how to make a statement about which factor is important and so on. Before we go to 2 raised to k design, which is the general design. So when you do something at 2 levels, so you might do, say, this is your factor and these are the values and these are the effects, and suppose you just do 2 levels, this and that. If the effect is just unimodal, it goes in one direction, then a 2-level design will give you a good answer. On the other hand, if the effect is not unimodal, it goes up and goes down. And if you just selected 2 levels, you might come to a conclusion that there is not much difference. But there is a difference because you missed the key point here. If you would have taken the level at this point, there is a big difference from here, right? So hopefully, basically what is going to happen is, this is where we say this is art of performance analysis. Why it is called art is because I cannot give a perfect scientific answer. It depends upon the system, which you know much better, your system. And 2 people reading the same or using the same system may have a different opinion. That's where it becomes art rather than science. So basically, you have to know your system, and you have to know that if system is like this, then 2 levels may not be good. If you really want to have 2 levels, then you should select a level here. If you don't, it might even be better to have 3 levels, where you have 1 level here and 1 second here and 3rd over there. Alright? So be careful when you use 2 levels, but here we are going to just concentrate on 2 levels and assume that the effect goes one way.
Then you are assuming that that effect is the same for all combinations, or at least the most combinations of the other factors?
Okay, so the thing is, the question is that if you're just going to do 2 levels here, then you are assuming that the interactions, etc., are all going to be correct. The answer is no. You are starting from the wrong base, all the answers will be incorrect. Alright? So this is I would have used 2 levels for this particular case. We use 2 levels as the first phase. First phase means that we figure out which are most important factors, which are least important factors. And the factors that are most important, we use a lot more levels. Then we use 4, 5, 6, 7, 8 levels.
What I mean is that when you plotted the 2 functions, you vary 1 factor and fix all the others to get that 2D graph.
But this is, I'm just plotting 1 factor, so okay, the good question. Actually the question is, this graph is, what about the other factors? There will be different graphs. Every time you change other factors, this graph will be different. Yes, interaction is a big problem. And so that is correct. So right now, let's just assume that they are on this side. And for most combinations, the factors are unimodal, either they're going up or going down. And again, this graph, this is just this is right now, here's the thing. At this point, we have not done any measurements. We really don't know. We're not even sure whether it is left or right. So we are taking a big chance. But what I'm saying is that if you start with 2 levels and large number of factors, then you can do a 2 raised to k design, which is much less than n times, n1 times, n2 times, n2, 3 times, big combination, right? And with this, at least you can figure out which are the most important factors, which may be incorrect still. But then you can do many more levels. Okay, then you will at least find the right area. Okay, so with that, let's just do some simple examples. So we have performance of a system in MIPS, which is million instructions per second, 2 memory sizes, 2 cache sizes, and these are the numbers that come out as the performance. So how do we model this? Well, we define 2 variables, XA, which is the memory, we will call it -1 if it is 4 megabyte, we call it +1 if it is 16 megabyte, and XB, the second variable, is cache size. It is -1 if it is 1K and +1 if it is 2K. So we define the variable XA and XB, and this is the Y value, which is the value of the performance. So we can write a very simple formula that Y is equal to Q0 plus QA XA plus QB XB plus QAB XA XB. And you can put these values for XA, XB and Y values, and you can solve it perfectly, exactly, because there are 4 unknowns and 4 equations. So there is no error, and the answer comes out that Y is always equal to 40 plus 20 times XA plus 10 times XB plus 5 times XA XB. Alright, given 4 unknowns and 4 experiments, you can exactly solve it. Now how do we read this model? This model says that the average performance of the system is 40 MIPS. And depending upon A, it could go up and down by 20 MIPS. If XA is positive, it will go up by 20 MIPS. If XA is -1, it will go down by 20 MIPS. And depending upon the cache size, the performance will go up by 10 or -10. Right? And during interaction, depending upon what XA and XB values you have, we have a change of ±5. Alright? And so now we, at least with this simple model, with this simple design, we can make a statement that the interaction is 5, that the effect of cache is 10, that the memory is 20. Now with this, at least, if you had X number of dollars of money, then you have to decide where to put the money. I would put the money on the memory first, because that is going to affect performance given that the memory is cost the same. Actually, memory costs much cheaper than the cache cost. So that is, you have to take that into account. But memory has much more effect on the cache in this example. Right? So we know, and then we know the interaction, which is 5. Now is 5 a big number or a small number? Again, that's an art, in the sense that it depends upon the system. And only the system engineers can tell you whether 5 is big or 5 is small. And so we cannot just say that most of the statistics books when we read, they let us feel that the statistics is a science, and anything which is not 90% confident doesn't pass by this phase. No. In fact, in our life, daily life, in our systems, we make decisions which we know could be 90% wrong. For example, if you have bought a lottery ticket, when you buy a lottery ticket, what is the chance of your being right? Like 1 in a few million? Right? So you're 99.999% wrong, but you are making a decision to take that risk because the reward is so great. Alright? So similarly here, whether 5 is good or small or large, it depends upon how much this system is worth, whether it is being used in a plane, whether it is being used in my computer, how much risk there is if we miss that point. So I cannot give you a rule for that, but I just want to tell you this is all the art part. However, what we can do is we can tell you a very simple method of analyzing this design, and that is by writing the combinations A and B, -1, -1, +1, -1. So these are the 4 combinations of A and B. Right? Everybody can write the Boolean table. So these are the 4 combinations for 2 factors at 2 levels. And then we can write a column AB, which is just the product of A and B. So you take -1 and -1, you get a +1. You multiply 1 with -1, you get a -1, and so on and so forth. And we add another column which is all 1s. with these 4 columns, we write down the y values here. So this 15 belongs to -1, -1, 45 belongs to 1 and -1, and so on and so forth. Now with this column, if I multiply that to the first column and add, I get 160. Multiply the second column, this vector and that vector, and we add, we get 80. And so on and so forth. We divide each of these by 4, we get 40, 20, 10, and 5. This is exactly the number that we had here. 40, 20, 10, and 5. Alright? So what we are saying is that you really don't have to solve any equations. If you are doing 2:2 design, you can do it very simply by making this table and multiplying and adding. And actually we do it in Excel. It's very easy to do it in Excel. You write a formula and then you just prepare the columns and then do the vector multiplication and sum it up and comes out the answer. So this is called sign table method, and all you have to do is prepare the column A and B, and then AB simply is a formula which says AB is just A times B. In Excel you can write that, and the first column is always 1. Alright? So everybody feels comfortable doing this somehow in Excel? Everybody knows Excel? Okay. So actually, believe it or not, all my students do this in Excel. When I wrote the book, there was no Excel. So usually you have to write a program in some language. But nowadays we don't need to write a program. We can just do it on in Excel. Okay. So we move forward from here. Now let's do something more interesting. And sorry for this statistics part, but this is rather simple. Is that we want to calculate what about the confidence interval. For confidence interval, we need the variations, variance, and so on and so forth. So let's calculate what is the variance. Variance of y is y minus y bar whole square divided by number of experiments minus 1. So this is generally the variance of y. If we just take the numerator and forget the denominator, then we can call it variation. So I'm playing with the word here. Variance is a statistical term. If you go to any book, they will tell you how to calculate the variance. Right? That is the first formula. But they are not going to use variance. They are going to use just the top part, and that is called variation. So the variation is yi minus y bar whole square added up. And this is called sum of squares total. This is sum of squares. You see, yi minus y bar squares total. SST. Now if you do that with this formula here which we wrote down, the formula is y is equal to q0 blah blah blah. If you square this and you do all that formula, you can prove, and this is proven in the book, I will not do that here, is that this sum of squares total has 3 parts. First part is 2 times square qa square plus 2 times square qb square plus 2 times square qb square qab square. So it can be divided into 3 parts. First part depends upon only the effect of A. Second part depends upon the effect of B. And the third part depends upon the interaction AB. So we call this sum of square due to A, sum of square due to B, and sum of square due to AB. And so basically we can divide into 3 parts. An interesting thing is now we can talk about percentages. We can say the total variation is so much, and out of that 10% is explained by A, 20% is explained by B, and so on and so forth. So let's do that for this example. In this example, the total variation will come out if you do yi minus y bar whole square is 2100. And that can be broken into 3 parts. The first part is 4 times 20 square, the second part is 4 times 10 square, and the third part is 4 times 5 square. So this is 400 times 4, 1600. Second part is 400, and the third part is 100. In terms of percentages, this is 76%, this is 19%, and this is 5%. Here's another interesting thing. You could go to your manager who doesn't know statistics, who doesn't know performance analysis, and they will understand this. You tell them, look, there are 2 factors, memory and cache. The effect of memory is 76%. the effect of cache is 19% changed. 19%. And the interaction between the two. Now this will take little bit explanation, but depending upon the combination of memory and cache, the difference is 5%. So most managers in this situation, when they see percentages like this, they clearly understand that they have to worry about one important factor here. Which is the most important factor? Memory. So 76%. And then they can make a decision whether they should go over 5%. Most managers will not go over 5% in real life. Now, statistician on the other hand will worry about significance and things like that, which we don't worry about here, because in practical life, really this is what matters. In practical life, I'm just talking about the real world there out there, where if given these three numbers, we would spend most of our time and money on the first factor, because that has 76% of the payoff. Alright? And so with that, so we know how to analyze. So now we understand one new thing. First of all, we know how to simply analyze a 2x2 design. Now we also understand how to assign percentages to the effect. Alright? And the percentages are simply proportional to the squares of the effects. If the square is 20, if the effect is 20, the percentage is 20 squared. If the effect is 10, percentage is 10 squared. Right? So that's another thing to notice, is that the effects have, basically the effect, the variation has a square of the effects. And so, can it be done for a real system? Yes. So that example that I made was pure example. I just put the numbers there for you to explain. But then what we also do in the classes is that we ask the students to apply it to their system. And when I wrote this book, I was teaching at MIT, so MIT students, they just applied it to their systems. And here's one example. This is called case study. Case study means this is a real thing. So I didn't make up any number here. Some students, they're doing PhD or research or whatever, and they were studying interconnection networks. Now, it's not really important for us to know what interconnection network is. That's not the purpose of this tutorial. But they applied it to this problem, and they have two different interconnection networks, omega and crossbar. Alright? And they have two different memory reference patterns, random and matrix. So, interconnection networks have to be evaluated. They have to figure out which one is better, for which they need to worry about the memory reference pattern, and they selected two, random and matrix. Now, there were several other factors that they fixed. So, they fixed number of processors at 16. Obviously, the interconnection networks are used to connect, multiple processors, multiple memories, right? So, number of processors fixed at 16. The queued requests were not buffered but blocked. Circuit switching was used, so packet switching and random arbitration. So, all of this is not relevant to the problem here, but it is important that you document all the things that you did not change, so that anybody who is later on analyzing or getting your results knows that you did not change this thing, and therefore if there is a change, the result will change. So all these restrictions they put there, infinite interleaving of memory, that means no memory bank contention. So and so on and so forth. So it's not really important for us to understand these assumptions, but it is important to document them. Because when you are doing a 2x2 or 2 by any number of design, you are simplifying lots of other stuff. And it's important to document that. So with that, they have two factors, A and B. Type of network is A, and that could be crossbar is -1, omega is +1. Second factor is the address pattern used. Random is -1, matrix is +1. And they wanted to measure three different things. They wanted to measure the throughput. They wanted to measure the 90% transit time, a transit number, and they wanted to measure the response rate, response time. So these are actually three different sets, so you can analyze. But the thing is, you write down the combination, 4 combinations, -1, +1, -1, plus, all those 4 combinations, and you can also write the column A and AB. And then for throughput, you can do the analysis, similar analysis you can do on the transit number, and then for the response time. The results are here. For throughput, these are the four numbers Q0, QA, QB, QAB. In terms of percentages, this means that QB is 77% and B is the address pattern. So what this is saying is that the address pattern affects throughput. Basically, the variation of throughput by 77% of the variation in throughput is due to the address pattern. Alright? 80% of the transient number is also due to the address pattern. And 87% of that is due to the response time is due to the address pattern. Now here's the interesting thing. Address pattern is something that you're not designing. You're designing interconnection network. And you're trying to decide whether I should use a crossbar or omega. And it turns out the answer is it doesn't matter. Really what matters is the address pattern. If you don't know the address pattern, then your results will be wrong. So that is an important conclusion, is that really the workload is so variable that has 80% effect on all of the three pattern, all of the three matrices that we were talking about. Right? So, I mean, if you were trying to sell your one of these interconnection networks, you could say, yeah, it looks like that one of them is better. Let's say T is QA is 0.05. Since it is positive, is QA plus 1 is better, and plus 1 is omega. So yes, omega is better than the crossbar. Alright? However, that is misleading, because you did not say that it is better only at 17%, where the memory would make a difference of 77%, and the interaction itself is 5%. Right? So this is the kind of thing that you can say from very simple design, whether it is the system or the workload which makes the difference. If it is the workload that makes the difference, then you really have to design the system. You have to have more control over the workload. Generally, we have no control over the workload. Once you design the system, you sell it, and the people will use it for something else. Right? So you have to just ask the customer first, oh, you want to do it for random memory pattern, or you want to do it for this kind of a memory pattern? And the customer says, I don't know. I really don't know what I will use it for. So you have a problem there, right? So this is the kind of result when you get into, then you have to go more into this as to how we fix the workload. Alright. So this is a real problem. So what we did so far was, all we did was 2:2 design, and we showed you an example, and we showed you a case study, which is a real thing. And by now, I have dozens of such case studies, because every year when I teach this, I have the students apply to their problems, and I get a dozen of these back to me, such case studies. And you can basically, if you're a student, if you're a professor, you can do the same thing, and you will get lots of such data, which helps you understand, helps you explain how we use these designs. Now what we can do is we can extend this to 2⁻k. So far we have only 2 factors, but we are going to have k factors. So first example is 3 factors. Instead of 2, now we have 3 factors: memory, cache, and the number of processors. And we can have each at 2 levels. So that would be 2⁻³ design. Right? And the model would be like this. It would be Q0 plus QAXA plus QBXB plus QCXC plus QABXAXB plus QACXAXC and QABCXBXC and QABCXAXBXC. Lots of parameters there, okay. How do you analyze this? Basically, you need to prepare 8 rows. When you have 2:3 design, you have 8 experiments. Right? So you put down all the Boolean combinations, -1. First you start with -1 plus 1, -1 plus 1, -1 plus 1, then -1, -1, plus 1 plus 1, -1, -1, and so on and so forth, like 0, 1, 0, 1, and then 4 at a time and 2 at a time and so on and so forth. Then you write down the columns for AB, AC, BC, ABC. AB is just product of A and B. AC is the product of A and C, and so on. right? So you prepare all these 8 columns, including the first one, which is all ones. Write down your 8 values, which are written here in a tabular form. You have to write down corresponding numbers. For example, first row is -1, -1, -1, which is -1 here, -1, number 14 right there. And then, 22 is where the first factor change, let's see, we just change A, B and C remain the same, so A is, in this case, A is the number of processors. So we change that and so on and so forth. So we write that down, and then the rest of the things is very similar to what we did before, is multiply this column, vector multiplication, add up, subdivide by 8, and you get the effects. And then you square the effects and multiply by the number of experiments. So 8 times QA square plus 8 times QB square and so on and so forth. And that says that the total variation is 100%. Out of that, 18% is due to factor A, 71% is due to factor C. Right? And the interactions are 4%, 1%, 2%, and 0%. Yeah. So the summary of this experiment would have been that the number of processors is the most important factor C. That makes a 71% difference compared to everything else. So if you want to put your money in to improve the performance, you put your money in the processor and not on the other two. Okay? And I showed you 3 factors design now. Can everybody do 4 factor and 5 factor? Does it make sense how to do the 4 factors? So how many columns there will be in 4 factors? How many? Anybody? I didn't hear. Can you say loudly? Not confident enough, huh? 2^4. If you have 2^3, 8 columns for 3 factors. For 4 factors, you will have 16 columns. For 5 factors, you will have 32 columns, and so on and so forth. So now you can see as you go by the number of factors, the number of experiments also actually, it turns out the number of rows is also exactly the same. This one has 8 rows, and 2:4 will have 16 rows. Right? But what we have done is obviously that the number is going up very fast, and then one would say that, well, how can we do this much? Yeah, but this is very easy to do in whatever is Excel or whatever you're using. The idea is now we know how to isolate the effects. Now we can make a statement, and this is an important thing, is that out of all these 16 numbers that we got, we can analyze it, and we can make a very simple statement that the effect factor C has so much effect. Now, if you have more time, if you need more, then we can say, but the next thing is A, which has 18%, and so on. So, if you are developing an algorithm, a distributed algorithm or distributed system or whatever it is, you know at least where to put your time in improving. So, generally, you are doing research. In the research, you have to not only show that your system is better than everybody else, but if you want to improve your system, you have to figure out what is the system, what is the condition under which it is better, just like here you figured out, and what are the other things that make a difference in performance, and then so maybe you can improve those more. Alright, so that brings us, summarizes the second part, and now we know 2^k design. This is called full factorial design, 2^k. And we can, and each at 2 levels. We didn't talk about more than 2 levels. Alright? Can compute main effects and all multi-factor interactions. So these things are all interactions. AB, AC, BC, ABC. And when you have 3 factors, you have some 2-factor interactions, you have some 3-factor interactions. And you can do computation very easily using sine table method. And you can do the allocation of variation. You can see how much variation is by each of those interactions and factors. Any question about this? Yeah.
Can it happen that when you do that, you find out that, for example, ABC is the factor that has
most important? Yeah. All right.
What does it mean then?
Yeah. What it means is that the factors are okay. So first let me repeat the question. The question was, if suppose the 71% was not here but there, ABC was 71%. In that system, you cannot make a statement about A, B or C alone by itself. You cannot make a statement about A, B or A, C or B, C about any two factors alone by itself, because the three-factor interaction ABC is so large that every statement about anything will have to include all three factors. Right? And generally there are very few systems which are like that. But if you have a system like that, then really what you are saying is that I cannot make a simple statement about one factor or any two factors. All three factors interact so much. All right? In terms of fertilizers and placebos in the medical field, basically what it means is that you cannot just make a statement about a fertilizer without worrying about what kind of land it is and what location it is and so on and so forth, whatever else there is, right? Similarly in computer science, when there is very high interaction, that means that you really have to control all the things and you have to know all of those things before you can make a statement. Good question. Any other question?
One more.
Yeah.
Just for curiosity, does it mean anything when the Q's are positive or negative?
Yeah. Alright, so when we did the square, all signs are lost. But when we did not do the squares, it turns out these numbers this is just an example, but let's go back to the real case study. Here, some numbers are positive, some are negative. Right? So what this means is positive means that the plus is better than the minus. Right? And negative means that the minus is better than the plus. Right? So we go back here, this is the plus and this is the minus. So when the effect is plus, means omega is better than the crossbar or matrix is better than the random. If the effect is negative, that means the other way around. So the sign has an effect and it depends. If you just change your definition, if you were to change the definition, call this as +1 and call this as -1, that's okay, except that all the numbers will come out the other side. And similarly for the interaction as well, the interaction is negative means that the combination, if A and B is positive, then this decreases the performance. In this case here. Alright. So, any other question?
I do have one.
Yeah.
When you're measuring the performance of the system, do you take into consideration the applications the customer is using, like the size and the type, and it might be taking a lot of memory from the system?
Okay, let me understand. I didn't understand the question, but let me just try to say. You are saying that when you do the experiment, it might take lots of memory from the system?
No. You just found out that the system is lacking memory.
It's lacking memory, yeah, okay.
Do you take into consideration that the customer might be using an application which is not suitable for that system, or that he might have options to change that application?
Okay, so let me see if I understood your question again. And we are talking about maybe something like, this is a good example. Let's go to the two-factor here. So our conclusion was that the memory has the most effect, but we assumed a particular application here. We did not really change the application. Now so that's why you have to make that list. This list is important because we used a particular application, and for that application this is true. If the customer changes the application, all bets are off. Okay, because in that case what we would do is we would take at least two different applications, make application a factor. You see? So in this example, in this case study, this is really an application. Address pattern is an application, right? So they had to make this because they fixed lots of other stuff, but they could not fix that because they didn't know. Right? So if you have a problem where you don't know what application that you're using, at least you take two applications, and generally if you have two levels, means you will take two extreme applications. One is very memory intensive and one is not memory intensive or something like that, and then do the analysis. So that will come out whether the application makes a difference. And if it turns out that this analysis that the application makes a lot of difference, then you just tell, please let me know beforehand as to what kind of application you have. Right? Okay. Alright, so we go to the next module, and we'll go to, let's see, we have a choice. We have to have a break, but break may not be ready right now, right? So we will continue up to 3:30, and then, we'll be in the middle of something, but we'll stop exactly where we are, doesn't matter. So now we are going to do 2 raised to k R design. What it is that we do each experiment R times. Okay, so we have 4 experiments or 8 experiments, but each experiment could be a measurement or a simulation. If it is a simulation, we will run the simulation R times. If it is an measurement, then we measure it R times. And we have to see whether the number changes every time we measure it, and it may or may not change. So the question is, if that is the case, then how we do all of the things that we have learned so far, how to compute the effects, how to estimate the errors. Now there are something new you can do which you could not do before. Now we can estimate the experimental errors. We can, we talk about the allocation of variation, but now we can also do confidence intervals and so on and so forth. So let us just do that. We have 2 raised to k experiments. Each of them is repeated R times. The model is still the same, but we have added one term extra here. So the model is y plus q0 plus qa times xa plus qb times xb plus qab times xa xb plus e. E is the error. So even if the xa xa value are same, there could be an error term. And so this is something that is not possible if you don't do replication. This is why it is important to do replication, because with replication, some of the factors that you did not control at all could have had an impact. Just like we said, room temperature could have an effect, and that will show up as an error. So here is a very simple way to do that. And that method is that we just take the same old method. So we have 4 2 by 2, and we repeat the experiment 3 times. And so we make a table AB minus 1 plus 1 minus 1 plus 1 minus minus plus plus, and then we write down AB, which is product of A and B. We write down I column. But we have 3 numbers now for each experiment. So what do we do? Well, one way to do this is to just take the mean. Instead of the 3 numbers, we write down the mean here 15, the mean of these 48, mean of these 324, the mean of these 377, and if we use this column to multiply with that column and add up, we get 164. Take this column, multiply with that, and so on and so forth. And then we divide by 4, we get the effects. So the analysis doesn't change much, except that now what we have is we have the effects. Q0 is 41, QA is 21.5, QB is 9.5, QAB is 5. But there is some more thing you can do, is that now you can calculate the predicted value. So if somebody gave you A equal to -1 and B equal to -1, and these are the effects that we already know, we calculated, then the predicted value is 15. However, you measure 3 different values. You measure 15, you measure 18, you measure 12. Therefore, the first one had an error of 0, the second one had an error of +3, the third one had an error of -3. Similarly, for the second set experiment, you had the errors -3, 0, and 3. Third one, you had 1, 4, and 5. You just subtract 24 from 25, you get a 1. 24 from 28, you get a 4. 19, you get -5. Alright? And so on. So basically, you have these numbers that were not there if you will not get those numbers if you didn't repeat. By the application, now we find out that the numbers 15 can change by ±3 here, 24 can change by somewhere from 1, 4, 5, like that. So there is some variation due to the factors that we did not control. Alright? So now we can take these numbers and say something about the errors. We can say something about what the mean error is, what the standard deviation of the error is, and so on and so forth, right? If you do that square and sum, you will find out that the total sum of squares has 4 parts instead of 3 parts before. We have QA square, QB square, QAB square plus the error square. And so if you do the calculation for the example that we did a minute ago, this one, you will find that the total sum of squares is 7032. Out of that, 5547 is this number. 2 raised to 2 times R. R is 3. 2 raised to 2 is 4. So 12 times QA square is this number. 12 times QB square is this number. 12 times QAB square is this number. And the sum of all errors is 102. Sum of squared errors. So if you take 0 square plus 3 square plus -3 square plus -3 square plus 0 square plus 3 square plus 1 square plus 4 square plus -5 square, add up the squares of all the errors, that will come out to 102. So now you can say that A has effect of 78%, 78.88, which is 79%. B has 15%, AB has 4%, and the errors have 1%. Well, you're in good shape because the factors that we did not control have only 1% effect. So that makes us feel better, because if that would have been 70%, then we would be saying, oh, 70% is due to the factors that we did not control. Alright, so we got to work harder there. But here it says that where errors are really small, and again A is the most important factor that we need to worry about. So now so one thing is that if you do replication, now we know how to analyze it and how to explain it to somebody who is not too much into statistics. That means our management, upper management. And this is how basically I learned all of this, because we had PhD and we were hired into a group called Performance Analysis Group in Digital Equipment Corporation. But the people who were making decisions about the systems, they did not know much about performance analysis. They didn't care. They just wanted us to tell them, which is the most important thing to do, right? So one of the things that we need in the real world is to be able to explain our analysis in very simple terms to the management. And so this is where you can say, well, 78% is due to A, and then we have taken care of most of the important factors because the errors are only 1%. All right. But we can do more. Now we can talk a little bit more statistics, and we can say that the errors are normally distributed. If you assume that the errors are normally distributed with some mean, 0, and some standard deviation, that will mean that the Y's are also normally distributed. Everything is normally distributed. And then the standard deviation of the errors can be calculated. Alright? By the exact formula. So the definition of standard deviation is, they teach in the statistics course, and I hope that you know it. If not, then, there are some few chapters before this we talk about that. Is that you take the squares, because the mean is 0 already, you take the squares of errors, divide by, in this case, 2 times 2 is actually 8. It's 4 times 2 is 8. And to divide by 8, and the reason you divide by 8 and not 12 is that even though there are 12 errors, only 8 of them are independent. If you give me any 8, these 8 for example, I can figure out these because they always add up to 0. So if you told me 0 and 3, I will know that the third one is minus 3. If you told me minus 3 and 0, I know that the third one is 3. If you told me 1 and 4, then I know that the third one is minus 5. So if only 8 are independent, so that is what we call degrees of freedom. Since there are 8 degrees of freedom, we divide by 8. So in any experiment where you have 2 raised to 2r, the degree of freedom is 2 raised to 2 times r minus 1. We divide by that, so we can calculate the standard deviation of this. It turns out if you know the standard deviation of the errors, you can also calculate the standard deviation of all the things that you estimated. So for example, QA has a standard deviation which is given by this formula, SE divided by square root of 2 raised to 2r. And once you have given the standard deviation, you can calculate the confidence interval. Now in this course here, we cannot really have time to go into confidence interval because that itself is a whole 1 hour lecture. But if you take my word for it, then what you have to do is you have to take the mean and the standard deviation and multiply by a number which you can find in the t table. So the book has a t table. You go to the t table and then you need to have 2 different values there. You need to have the degree of freedom and the confidence and so on and so forth. It's kind of complicated. But anyway, if you know all this confidence interval stuff, then this is very trivial stuff. Okay. So what you can do is you can calculate the confidence interval, and then one very simple thing which many statisticals don't point out to you is that if the confidence interval includes a 0, that means it is not significant. It is not statistically significant. So let me just show you an example and that will be better. So for the example that we had, we found out that the sum of a square error was 102. We divide by the degree of freedom, take the square root. So the standard deviation of the error is 3.57. Then we can calculate the standard deviation of all the effects, which is exactly 1.03 by just plugging into the formula. We look up the t-value from the book at 95% confidence interval. Why 95%? Just arbitrary. Okay, actually this is this is at 90% confidence interval, but since it could be positive or negative, we take 5% error on the top, 5% error on the bottom. So we use 0.95 to look into the table. So why 90%? Because this is very arbitrary. In the real world, you have to be careful. If you're designing a plane, you would not use 90%. Right? You would use 999.9996 nines, 7 nines, something like that. Okay? If you're designing a laptop or something, maybe you could do 90%, 99% or something like that, because the laptop could be used for some. If you're designing a toy, maybe you could do 90%. So that's an art. We cannot just give you a perfect number. Alright? So once we know that we want to use 90% confidence, you can look at the p-value and you can calculate the confidence interval by just plugging in the value of the effect plus minus 1.86 times the standard deviation, which is 1.03. So plus minus 1.92, and for these different factors that we calculated, these are the values 39 to 42, 19 to 23, 7 to 11, 3 to 6. It turns out none of them have a 0 in between. So because generally we just look at the sign. If this was minus 39 to 42, we know that it's going to cross the 0. And if it crosses the 0, means this is not significant. That means it could be 0 itself. In this case, these things are basically all significant. So all effects are significant, and that is, and then also you know how confident you are basically. So the important thing is to look at the range, and the range exactly is 1.92. So the least confident is like this one here, because it goes from 3 to 7 almost, the interaction, but it is basically also very small. So that's, so this is where I stop doing statistics, because something which is not important, I really don't care whether it's significant or not, right? And the importance comes from the percentage. This is importance, right? 78% is very important, this is less important. What we are talking about is significance, statistical significance. A lot of other people, a lot of statistics people actually in particular, they give a lot of importance to the significance. Right? But we don't.